Deep dive into scikit-learn's IsolationForest, unveiling the anomaly detection powerhouse. The IsolationForest algorithm, implemented in scikit-learn as IsolationForest, is a powerful tool for anomaly detection. It leverages the concept of isolation to identify outliers in a dataset. Let's break down the algorithm's core principles, implementation details, and real-world applications. 1. Conceptual foundation: isolation, not outlier scoring. Core idea: instead of explicitly defining what an outlier is, IsolationForest focuses on identifying data points that are easily isolated from the rest of data. It relies on the intuition that anomalies are often more easily isolated than normal data points. Isolation procedure: the algorithm builds a collection of randomly constructed decision trees called isolation trees. Each tree is built by recursively partitioning the data using randomly selected features and thresholds. The path length of a data point within a tree, number of splits required to isolate it, is a measure of its isolation. Anomalies tend to have shorter path lengths as they are often isolated with fewer splits. Ensemble averaging: the algorithm constructs multiple trees and averages the path lengths across them to obtain a robust isolation score for each data point. 2. Building blocks: understanding the isolation tree. Randomized feature selection at each node of the isolation tree. A feature is randomly selected, and a split is made using a random threshold within the range of that feature. This randomness helps isolate anomalies by exploiting the unusual nature of their feature values. Stopping criteria: trees are grown until a certain depth limit is reached or all data points in a node belong to the same class. This prevents the trees from growing too deep and becoming sensitive to noisy data. Path length computation: the path length of a data point is calculated as the number of nodes it traverses from the root to the leaf node. Shorter path lengths signify easier isolation, often indicating anomalous data. 3. The isolation score: quantifying anomalousness. Score interpretation: the final isolation score of a data point is the average path length overall the isolation trees. Lower scores closer to 0 indicate higher likelihood of being an anomaly, while scores close to 1 suggest a typical data point. Decision boundary: the algorithm typically assigns a score to each data point, allowing for a flexible threshold to be chosen for identifying anomalies. This threshold can be based on the desired sensitivity of the detection, i.e., how many false positives are acceptable. 4. Advantages of IsolationForest. Robustness to noise: the random feature selection and tree construction make the algorithm resistant to noisy data and outliers themselves. Scalability: IsolationForest scales well to large datasets, as building trees on small subsets of features is computationally efficient. Non-parametric: the algorithm does not require prior assumptions about the underlying data. Distribution, making it suitable for complex and diverse datasets. Interpretability: the decision paths within isolation trees can be visualized to gain insights into the factors contributing to anomaly detection. 5. Practical implementation usage in scikit-learn. Initialization: IsolationForest nestimators 100. Contamination 0.1. Behavior: new. Nestimators: number of isolation trees to build. Contamination: estimated proportion of outliers in the dataset. This influences the threshold for anomaly detection. Behavior determines how the algorithm treats previously unseen data new for anomaly detection. Old for fitting only. Fitting model. Fitx. X the training dataset. Prediction model. Predictix. Returns 1 for normal data and -1 for anomalies. Anomaly score model. ScoreSampleSex. Returns the isolation score of each data point. 6. Real-world applications beyond the basics. Fraud detection, identifying fraudulent transactions in financial datasets. Network intrusion detection, identifying malicious network activity. Medical diagnosis, detecting unusual patterns in patient data for potential diagnoses. Outlier detection in sensor data, identifying sensor failures or unexpected events. Data cleansing, removing outliers from datasets to improve the performance of other machine learning models. 7. Key points to consider. Hyperparameter tuning, experiment with contamination and estimators to optimize the performance for your specific dataset. Feature scaling, consider scaling features before fitting the model to prevent bias due to differing scales. Understanding the anomaly threshold, the contamination parameter provides a general guideline, but you may need to adjust the threshold based on the specific application and tolerance for false positives. 8. A final word. IsolationForest provides a powerful and versatile tool for anomaly detection. Its ability to efficiently identify outliers in diverse datasets makes it a valuable asset in various fields. By understanding the core principles, implementation, and considerations, you can effectively leverage IsolationForest for your anomaly detection needs.